Okay, welcome to Chem 127, Lesson 1A1. Today, in this first lesson, we're going to learn about how the atmosphere is put together. Formally, we would call that physical and chemical structure of the atmosphere. Physical structure just means, where is the air? How does it vary? What is the temperature like? What do we call the various layers of the atmosphere? The atmosphere is layered. The second part of that is the chemical composition, which means what chemical substances consist of the air, and to do that we need to know a little bit about how we talk about various chemical substances, which means we need to learn about what chemical formulas mean and the like. Sort of a quick little review of high school chemistry. This material has kind of trickled through the first 10 sections of chemistry and contexts. I will ask you homework questions about it on homework number 1. I will also post the chapter 1 problems to chemistry and context, and these are some problems here which reinforce some of these concepts. You can regard these as optional. Again, the way to do well is to make sure you can do my homework assignments. Okay, moving forward here. Okay, with this lesson on the D2L page, you should have seen a link to some handouts. The first thing I'm going to talk about here is this handout, which has a picture of the atmosphere on it, and a graph of the temperature and a graph of the pressure. And the first of those things, the first part of the lecture, I'm going to talk about those. Before we get into that, let's just be very general here. Chem 127 is a non-majors environmental chemistry course. We focus primarily on one issue, but it is an environmental chemistry course in the broadest sense. And for me, there's 3 big primary questions, and I just figured I would review these to kind of bring us in from the broadest considerations possible into the issue we're going to talk about here eventually, which is global climate change. Now, the first issue for an environmental chemist is, what is out there? In other words, when you look at nature or a part of nature, say the air or a lake or a canyon or a farm field, what is the chemical composition? What chemical substances are there? And environmental chemists spend some time analyzing those places to find out what chemical substances are there. The next question is, is it still changing? In other words, beyond the sort of processes by which the Earth evolved and came to be what it is today, are there things right now that are causing change in that chemical composition, like pollution, or maybe natural things like biological productivity of some kind? What really makes this environmental chemistry and not ecological chemistry or geological chemistry is the role of humans. And in this instance, an environmental chemistry is really focused often on question number 3 here, and that is, what is the role of human activity on the chemical composition of one of these systems? In our case, when we talk about global climate change here, the sort of basic fundamental hypothesis is that the use of fossil fuels for a century and a half or so, maybe really 2 centuries, has that caused the chemical composition of the global atmosphere to change in a way such that it's affect the temperature of the planet. So again, then you can see how climate change really fits into this broader scope of environmental chemistry. Okay, moving on to that picture there. Okay. This is a picture of the atmosphere. This is sort of like a vertical slice. So this is the top of the air up here. This is the surface of the Earth down here. And then this is a plot of the pressure. This is really kind of a backwards graph, and that normally you would say, I'm going to have my x-axis here, the thing that I'm varying, and I want to see how the thing that I'm talking about varies on the y-axis. But here, I think this is chosen to be this way because, well, we want to know how pressure varies with altitude. Altitude is up to us. So this is kind of a backwards graph if you're paying close attention. What this shows is how the pressure of the air changes as we go from bottom to top. Now, let's just talk about what pressure is first here. Okay, formally, pressure is force over area. That is not only how hard something pushes on something, but what is that characteristic push per unit area. In other words, a mattress will exert the same amount of force on the floor of your bedroom, but will exert a lot more pressure if it's on a bed frame with 4 posts, because all that force will be concentrated into, 4 little things where there's bed posts. So that's the idea. Now, think about pressure of a gas or a liquid or some chemical substance. One of the things to realize is that this is this average effect that comes about from feeling a bunch of little molecules flying around hitting your skin. So as we feel air pressure, what we're feeling is little air molecules bouncing off our skin billions of times a second. So molecules are very small, and they're constantly sort of pelting us like little pellets. And we feel that as sort of a constant force because it's so fast and so continuous. What I want to convince you of here, there's lots of things that can affect this pressure, but really what I want to convince you of is that this graph is really a measure of how much air is where in the atmosphere. So first of all, let's just talk about units that you might see for the pressure. We aren't going to do a lot of quantitative stuff with pressure, but perhaps the most common unit for pressure is the unit of an atmosphere, which is kind of a strange unit. You don't encounter that from day to day, but somebody at some point walked outside at sea level and said, the pressure is about like this, let's call that 1 atmosphere. And then half an atmosphere would be half as much pressure, and so on and so forth. More formally, meteorological types and chemists in some instances will use units of bar, and lo and behold, 1 bar turns out to be about 1 atmosphere. Often on a weather map, you'll see this in units of millibar. Milli means 1/1000th, so 1,000 millibar is 1 atmosphere. So beyond, on the right-hand side of the slash here, is what about 1 atmosphere pressure is in these units. On this graph, is plotted in a unit that chemists typically use, and I think nobody else uses them besides chemists, which is torr. In high school chemistry, you might have known this as a millimeter of mercury. But anyhow, 760 of those torr is an atmosphere. So you can see down here at about sea level, that this graph is 760. And then you can see that it continuously goes down as we go up. Now let's just talk about some of these other things that can affect pressure here first. My little square here is kind of a crummy representation of a sample of gas for which the pressure is 1 atmosphere. And we just want to sort of think about what happens as we change the physical properties of this little vessel holding gas. Remember again that pressure comes about from molecules colliding with the outside of the container. One of the things we might do is heat the sample. If we heat the sample, those molecules are going to move faster. They're going to hit the container a little bit more, with a little more velocity, a little more energy, and that's going to exert more force, and the pressure will go up. One of the things we could possibly do is shrink the size of the container, so there isn't going to be more molecules in there or more energetic molecules, but they're going to be in a smaller space and they're going to hit the walls of the container more often, and again the pressure will go up. Again, what I'm trying to convince you of here is the other thing is that if we added sample, and notice that I made this a little darker to say there's more gas in here now, just like when you add air to a tire, lo and behold the pressure goes up. Now, as we'll see in a second, these temperatures changing as we go up here too, but that's not anywhere near as big of a factor as this bottom one here. And what this sort of shows is that as we go up, this pressure decreases very quickly and the air gets very thin up here. Now, when you're flying in a commercial airliner, you're somewhere up here between 10 and 15 kilometers. And you'll see that airliner is riding on about 200 torr of air, which is about a quarter of an atmosphere. So you get that big 757 floating on a quarter of as much air as it took off, which is kind of creepy, but there's also less air keeping it from moving forward faster, so it can fly faster as well. So that atmosphere tapers off pretty fast. And in the lower layer of the atmosphere, called the troposphere, that we'll talk about in a second, which is this region here, actually holds 90% of the air. There is a famous physicist, atmospheric physicist by the name of Hoyle, who has a funny saying that says, outer space isn't that far. You could get there by, a few hours drive if you could drive your car straight up. Okay, and this, this is just a few hours drive. Let's see, 100 kilometers is 60 miles. So here's an hour's drive, and you're out of the atmosphere if you're moving pretty fast. So there.